Electricity is one of our most faithful servants. It gives us light. It starts our cars, has unlimited in aviation, circles the globe with entertainment. It cooks and refrigerates our food. These represent few of the innumerable applications of electricity. Electricity at work. But what is electricity, and where does it come from? To answer these questions, let's look in on the world of electrons. The entire universe is composed of matter. A basic concept of the structure of matter is essential for the understanding of electricity, because the very force that holds matter together has an electrical nature. There are many different substances, each a combination of some of the 92 known chemical elements. Just as yeast, flour, salt, sugar, and shortening are the ingredients used in making bread, so are the 92 elements the ingredients of all matter. And if one of these elements is reduced to its purest, final form, its smallest unit would be an atom. No one has ever seen inside an atom. However, we think of it as a system of electrons circulating around a heavy nucleus at almost inconceivable speeds. In order to explain the principles with which we are concerned in this story, let's assume that we can stop the action within the atom. And further, let's acknowledge that this is a symbol representing the atom and not an attempt to show it as it actually is. It is impossible to show the correct relative proportions of an atom on this screen. For example, if an atom could be as large as the United States, one of its electrons would be only about 100 feet across. Therefore, to tell our story, we must resort to a symbol. Then we can think of the atom as being a group of relatively light, small particles arranged around a heavy nucleus. These are particles of electric energy. The lighter ones, the electrons, are negative electric charges. And the heavier one, the nucleus, carries positive charges. Normally, a state of balance is maintained within the atom by a positive charge in the nucleus equal to the total negative charge of the electrons. And when the atom contains its normal number of electrons, it is said to be in electrical balance, to be in a neutral electrical condition. It is possible, however, to disturb this normal balance, whereupon the unbalanced atom assumes an electric charge. Too many electrons will produce a negative charge. Too few will throw the balance onto the positive side. In order to visualize better the effect of this, let's introduce a color code in which the positive charge, or an absence of electrons, is represented with red, and the negative charge, a predominance of electrons, with blue. Then an object that is in electrical balance will be purple, an equal part of each of the positive and negative charges. We have been concerned so far with the electrons within individual atoms. Now let's see what happens when two or more neutral atoms come together. The outside electrons will no longer move exclusively within their original atoms, but will circulate about both atoms at once. And if we bring many such atoms close together, as in a piece of metal, then many electrons detach themselves from their original atoms and move freely throughout the metal. As long as the metal has its normal number of electrons, it is electrically neutral. But like an individual atom, it can lose some of its electrons and become positively charged, or it can pick up more than its normal number of electrons to become negatively charged. The electrons always try to get from a negatively charged body to one that is positively charged in relation to it. And if they are brought together, the electrons will flow from one to the other until both objects are equally charged. The establishment of unbalanced charges in matter is, in all instances, the principle of the generation of electricity. To illustrate further this principle, let's analyze the action within a cell, a simple source of electric energy. A piece of zinc is suspended in a suitable container. Its atoms are neutral until a chemical solution is added. Then some of the zinc atoms go into the solution, leaving a few of their electrons behind in the metal. The zinc becomes strongly negatively charged. Now a piece of electrically neutral copper is put in a chemical solution in another container. The copper will become very weakly negative. Since the copper has a smaller negative charge, it is positive with respect to the zinc. And if the two metals are connected, the electrons will surge from the zinc to the copper, and the charges will become equalized. This momentary current has little practical value. However, if we now connect the solutions, the charges in the solutions will become equalized, and the metals or terminals will be charged. We will then have an unbalanced condition of the electrons in the metals capable of producing a continuous flow of useful electric current. All of the work performed by electricity requires a flow of current. So let's see what principles are involved when current flows. There are three related to the flow of electricity. They are pressure or voltage, current intensity, and resistance. First, let us consider pressure. With nature always trying to maintain an electrical balance, there is a tendency for any negatively charged object to throw off or repel its excess of electrons, and for a positively charged object to attract electrons. This urge to maintain an electrical balance is potential electric energy. And since this potential energy is a repelling and attracting urge caused by opposite charges, its force or pressure is equal to the difference in the charges. It is called the difference in potential or potential difference. The unit of pressure or potential difference is the volt. The voltage, then, is always the potential difference at the negative and positive terminals of the source of the electric energy. It represents the difference between the number of extra electrons at the two terminals. And when a suitable path is provided, the potential difference causes the electrons or current to flow from one terminal through the conductor to the other terminal. To explain how this works, let's review the action of the atoms and their electrons in a piece of metal, where we saw swarms of electrons moving freely in all directions about the atoms. Substances in which this takes place are good conductors of electricity. If an outside electric pressure or voltage is applied to a conductor, the electrons will move predominantly in one direction. The effect is that electrons move from the negative to the positive terminal. This is the electric current. The unit of electric current is the ampere. 1 amp, now hold on to your hat, 6,300,000,000,000,000,000 electrons passing any given point in 1 second. Current, or amperage, then, is the number of electrons that pass a given point in a given time. And now the third factor, resistance. This factor is controlled by the nature of the material through which the electrons flow. Again, going back to the motion of electrons in a metal, we said that they moved freely about and among the atoms. However, even in the best of conductors, some of the electrons collide with the atoms, tending to retard the movement of the electrons. This is the cause of electric resistance. Collisions are more